Good evening to the Vice Chancellor and Principal, Professor Tawana Kupe, our speaker this evening, Professor Njoroge Gitau, members of the UP Executive, Deans, our Deputy Deans, Professor Naidu, the Head of Department for the Department of Electrical, Electronic and Computer Engineering, and our other heads of department, academic and professional staff, colleagues, family of Professor Gitau, ladies and gentlemen. It is indeed wonderful to have so many of you attending today's inaugural address. Welcome to this inaugural lecture to be presented by Professor Njoroge Michael Gitau, entitled Effects of Changes in the Energy Mix and Types of Loads on Future Power Grid. We are indeed privileged to have our Vice Chancellor and Principal, Professor Cooper, to officiate at this inaugural lecture. Please join me to welcome Professor Cooper to formally open this event and introduce the speaker. Professor Cooper.
Good evening, good afternoon, good morning. In case there are people across the world listening to this distinguished lecture by our inaugurating professor, Professor Michael Njoroge Gitau, Dean of the Faculty of Engineering and Built Environment, Professor Maharaj, and all who are watching this virtual address. Professor Michael Njoroge Gitau graduated with a first-class honors degree from the Department of Electrical and Electronic Engineering, University of Nairobi, Kenya, in December 1984. He then worked for the Kenya Railways Organization as an electrical engineer between 1985 and August 1988. Between September 1988 and August 1990, he worked as a teaching fellow in the Department of Electrical and Electronic Engineering, University of Nairobi, his alma mater in Kenya. In September 1990, he was awarded a Commonwealth and Foreign Office Chevening Scholarship to pursue PhD research in power electronics at Loughborough University in England in the UK. He graduated with a PhD degree in power electronics in April 1995. Between January 1995 and 1996, he worked as a lecturer in the Department of Electrical and Electronic Engineering, again at his alma mater, University of Nairobi in Kenya. Between February 1996 and October 1997, he worked as a postdoctoral fellow at the Department of Electrical and Electronic Engineering, University of Stellenbosch, here in South Africa. He joined the Department of Electrical, Electronic and Computer Engineering, the University of Pretoria, as a senior lecturer in November 1997. In January 2001, he was promoted to the rank of associate professor. He was awarded a Commonwealth Fellowship that allowed him to spend 6 months as a visiting professor in the Department of Electrical and Electronic Engineering, Loughborough University, his other alma mater, between October 2004 and April 2005. He also spent 3 months as a visiting professor at Université du Québec, Trois-Rivières, Quebec, Canada, and Tennis Technological University, USA in 2014. He was promoted to the rank of professor in 2020. He's a senior member of the Institute of Electrical and Electronics Engineers, IEEE, and a registered professional engineer in South Africa. He has supervised to completion 3 PhD and 16 master's research students and published 59 journal and conference articles as well as a book chapter. He's also a reviewer of several IEEE and IET journals, and in 2020 was a guest associate editor for a special edition of the IEEE JEE STPE journal. His research interests are in analysis, modeling and control of power electronics converters, conducted EMI generation and mitigation techniques in DC-DC converters, converters for integration of renewable energy resources into the grid, and converters for realizing DC grids. Ladies and gentlemen, I present to you tonight our inaugurating professor, Professor Njoroge Michael Gitau. Professor Njoroge Michael Gitau, your audience tonight.
The Vice Chancellor of the University, Dean of the Faculty of Engineering, Built Environment, and Information Technology, the academic, members of the academic community, friends and colleagues, greetings to you all and a word of gratitude for being present tonight. And also special thanks to the Vice Chancellor, Professor Tawana Kupe, and the Dean of Engineering, Built Environment, and Information Technology, Professor Sunil Maharaj, for officiating at tonight's function. The title of my presentation tonight is Effects of Changing Energy Mix and Types of Loads on the Power Grid. A brief outline of the talk is there'll be a short introduction. Then I'll look at present-day energy mix and loads. I'll also look at present-day power generation and energy delivery systems. Then I'll look at future energy mix and loads and the effects on the grid, possible future grids and architectures, and a mention of relevant research activities by the Power Group at the University of Pretoria. And lastly, I'll look at the challenges that will be faced before DC grids can be realized, and also concluding remarks. Power grids evolved in the 20th century based on AC generation, transmission, and distribution. And for many decades, fossil fuels have dominated as the primary energy sources in all sectors of the economy. Fossil fuels are partly used to generate electricity needed in many sectors. However, in the industrial, mining, and agricultural sectors, there's a high direct utilization of fossil fuels. More recently, concerns about harmful emissions from fossil fuels have led to renewable energy sources being introduced into the energy mix. It is therefore important to determine how changes in the energy mix and types of loads will affect the grid. Data is available on the energy utilization, and we are in a position to determine the energy mix based on this available information. If we consider the total global situation and taking the year 2010 as a reference point, what we see is the following. In 2010, fossil fuels accounted for 87.3% of the energy mix. Nuclear had 4.6%, and renewable energy sources accounted for 8.2%. About a decade later, in 2019, the proportion was 84% fossil fuels, nuclear energy, that was 4.5%, and renewable energy sources, 11%. So we can see that in that period, not much change, there was not much change in the energy mix. In the case of South Africa, the picture was not very different, with fossil fuels again dominating. And if we look at the period 2000 and 2016, what we see is that between 2010 and 2016, the energy mix remained fairly constant, with the fossil fuels accounting for 95.7% of the total energy mix, nuclear 3.4%, and renewable energy sources just a mere 1.5%. So what can we say about power generation from fossil fuels and also nuclear power? Advantages are they are good for baseload. However, they do have some disadvantages, and these include very low input-output efficiencies as thermal processes are employed. We also have high levels of hazardous emissions from fossil fuels, also a high utilization of water. In the case of fossil fuels, one of the problems is high running costs, while for nuclear, we have high decommissioning cost. We also have a problem of environmental risk during extraction, transportation, and utilization of the fossil fuels. And looking at large hydropower plants, the advantages include low operating costs. Also, large dams play a role in flood control, as well as water being available for other uses. But on the downside, the large hydropower dams entail flooding vast areas, and this poses a threat to local ecosystems due to loss of species. In addition, the large bodies of water give rise to microclimate changes. And turning my attention to power generation from renewable energy sources, we see that advantages include low initial cost, primarily because the prices for the solar panels and wind generators have fallen significantly in the last 1 decade. Power plants based on renewable energy also have low operating costs. And in the case of solar thermal power plants, they do have characteristics that are similar to conventional power plants, making them suitable to supply base loads. But on the downside, due to the intermittency of the solar energy sources, sometimes there's a need to employ energy storage systems, and this translates into high initial cost. Also, wind and solar farms occupy large surface areas. And what about the present-day loads? If you consider the residential, commercial, and industrial sectors, many of these loads are DC or electronic loads, and as such, they require AC to DC converters to connect to the AC grid. These converters add to the initial cost, as well as decrease the system efficiency. We also have, in addition to the DC loads, some AC loads, and these include single speed AC motors that are widely used in industry. And as well as that, we have heating loads that utilize fossil fuels directly. In the transportation, agricultural, and mining sectors, majority of the loads utilize fossil fuels directly. For example, your internal combustion engines. But we do have a small number of hybrid and electric vehicles. In addition, we have electric trains for passenger and goods transportation, as well as in mining activities. And what can we say about the present-day power grid? It can be divided into 4 main areas. And these are generation, transmission, distribution, as well as the load centers. And to integrate or interface these different parts together, we require magnetic transformers because they allow ease of voltage level translation, and the benefit of this is to help reduce overall losses within the power grid. And looking at the power grid, we see that we have a small number of DC grids also integrated, but these are only point-to-point and mainly used in long transmission lines. But more recently, DC subsystems have been used to connect renewable energy sources to the AC grid. But for the transportation of the fossil fuels, we utilize pipelines, road and railway transportation systems for this purpose. And looking at the assets of the AC grid, the key assets include the generators and transformers, electromechanical protective equipment. We have thermal power generation processes that utilize boilers and steam turbines, but the hydropower require water turbines. And in the case of solar thermal power generation, in addition to the boilers and steam turbines, we require collector dishes and molten salt towers. The AC and DC transmission systems comprise mesh networks. For the AC networks, dynamic stability concerns do limit power transfer capability. But we do have a few wind and solar panels that are integrated into the distribution system. For the DC transmission systems, the assets include DC cables and lines. We also have line frequency power electronic converters. These are your rectifiers on the generation side and inverters that connect the DC lines to the AC grid. The AC protection equipment, but unlike the AC transmission systems, DC transmission systems do not suffer from dynamic stability limitations. As a result, power transfer is only limited by thermal considerations. There's also another type of DC technology, which is referred to as voltage source converter-based technology. However, this is not widely adopted because at the moment, DC protection equipments are still very expensive. And hence, we see there's a need to bring down those costs before that technology can be widely adopted. In looking at the future or the possible future energy mix, this will be influenced by the policies that governments will adopt. So we'll look at two scenarios, and these are one where policies are not favorable to renewable energy sources, and the second scenario is when governments adopt policies that are favorable to renewable energy sources. Again, looking at the total global energy mix, we see that if we take the year 2020 as a reference, fossil fuels accounted for 81.6% of the energy mix, nuclear 4.7%, and renewables 13.7%. And for projections that assume policies do not favor renewable energy sources, we see that in the year 2040, projections are that fossil fuels will account for 77.7%, say 78%, nuclear around 5%, and renewables 17.3%. So we can see that if policies are not favorable to renewable energy sources, we will not see a big change, compared to the current situation. So what can we deduce based on those projections? We see that relative to the year 2020, renewables will increase by a factor of 1.53. Coal usage is projected to remain at the 2020 levels. Nuclear will grow by a factor of about 1.3. Natural gas, an increase of about 1.4. Petroleum and other liquids will increase by a factor of 1.1, so not a big change there. And the total energy consumption projected to increase by a factor of 1.22. However, with the total energy consumption, the actual growth will be a function of the economic activities. And now looking at policies that are favorable to renewable energy sources, I will use the future energy mix for electric power generations to see what might happen in the future. If you take the year 2020 again as a reference, the fossil fuels accounted for 46.8% of the energy mix for electric power generation. Nuclear accounted for 17%, that is globally. Renewables, 36.2%. But if we exclude hydro and geothermal power from the renewables, the percentage was 12.7%. And this shows that in the current energy mix is the geothermal and hydro that dominates in the renewables. So with policies that favor renewable energy sources, the projections are that in the year 2040, fossil fuels will account for 14.8%, say around 15%, nuclear 9%, and renewables around 76%. The total energy consumption is projected to grow by a factor of 1.65 relative to the year 2020. Renewables will increase by a factor of 3.5, but if you exclude hydro and geothermal, renewables will increase by a factor of 7.3. So we can see that the renewables will grow substantially, and as a result, it's expected that DC subsystem in the grid will track the increase in the renewables. For the case of South Africa, or if you look at the situation in South Africa, again, considering the two policy scenarios, we see that if policies that do not favor renewable energy sources are adopted, fossil fuels will account for 56.2% of the energy mix in the year 2040, nuclear about 22%, and renewable energy sources another 22%. However, if policies favoring renewable energy sources are adopted, then the composition will be 24% fossil fuels, nuclear 3.3%, and renewable energy sources will increase to 72.3%. So we can see the influence of the policies that are adopted on the energy mix. And what can we deduce from those figures? Total energy consumption is projected to rise by a factor of 1.62 by, relative to the year 2020. But if business as usual policies are maintained, renewables will increase by a factor of 3.5. Renewables excluding hydro will increase by a factor of 5. Whereas if optimal policies are followed, renewables will increase by a factor of 10.5. So we can see the influence of policies in the energy mix. While if you exclude hydro, the increase in the renewables will be 15.4 times. Fossil fuels, on the other hand, are projected to fall by just over 50%. And this will translate into a big increase in the DC subsystems in the grid. There's also another possible scenario, and this is where all the energy comes from renewable energy sources. This would require developing virtual power plants. It will also open opportunities to develop modular grid structures. Currently, Saudi Arabia is building such a system in a new city referred to or to be known as NEOM. And the projected installed capacity in that city will be actually comparable to the current installed capacity in South Africa. So looking at the future energy mix, we can deduce the following. Irrespective of policies adopted, the share of fossil fuels will decline. This should translate into a high or higher input-output efficiencies, but if replaced with renewable energy sources. It should also translate in lower running costs in the overall power generation process. In addition, lower levels of hazardous emissions, as well as a lower demand on scarce water resources. For nuclear power, all predictions suggest that power generation from nuclear will at best remain at the current levels. And for nuclear power to play a role in the future, we require safer designs to mitigate against current concerns. However, high decommissioning costs will remain a problem unless newer designs that mitigate against the high decommissioning costs are developed. On hydro and geothermal power, existing large hydropower plants will continue operating. However, mini and micro hydropower plants could be adopted as part of distributed energy sources. These should pose fewer problems compared with large hydropower plants, as they will not entail flooding large areas. There's also high potential for geothermal power in a number of regions around the globe, And these include areas like New Zealand, eastern parts of Russia, around the Caspian Sea, in Iceland, and also in the Rift Valley of Africa. As for direct utilization of fossil fuels, this would decline in all sectors of the economy. And this should translate into higher overall efficiencies if replaced with electric power from renewable energy sources. But it will translate into a decrease in overall efficiencies if replaced with electric power from fossil fuels. We should also witness a reduction in environmental risk associated with the extraction, transportation, and utilization of fossil fuels. However, it will be necessary to expand the electric grid to cater for additional electric power generation that will be required. On renewable energy and hydrogen, power generation from renewable energy sources will be more widely adopted in many countries. And this will translate into an increase in the number of DC subsystems in the grids. And to address the intermittency problems associated with the renewable energy sources, it will be necessary to integrate energy storage systems within the grid. This creates an opportunity to utilize the available distributed battery storage systems. And here we are looking at batteries that are found in electric vehicles, as well as in the residential and commercial sectors. However, it will be necessary to develop new techniques for optimal utilization of the distributed energy storage systems. Hydrogen production is used as a form of energy storage in the case of renewable energy sources. However, the current processes have very low overall efficiencies. Hence, it will be necessary to develop new types of energy storage systems for grid applications. And with adequate energy storage, renewable energy systems will attain similar characteristics as those for conventional power stations, but minus the disadvantages of conventional power stations. When it comes to future loads, most of these will be electronic in nature in the residential, commercial, and industrial sectors. This type of loads favor DC power distribution. So if DC power distribution is adopted, this will remove the need to incorporate AC to DC power electronic converters. And as a result, this will lower the cost while increasing the system efficiency. In the transportation, mining, and agricultural sectors, the loads will be overwhelmingly electronic. In countries like China, they have set targets of about 70% of new electric vehicles to be sold by the year 2030. In Europe and the United States, the target is for at least 50% of electric vehicle sales by the year 2030. However, slow charging times have been seen as a discouraging factor or to discourage fast adoption of electric vehicles. So to reduce charging times, it will be necessary to develop big DC power supplies for supercharger stations. Hydrogen fuel cell vehicles, if adopted, will require electrolyzers for hydrogen production. And to derive maximum benefits, the electrolyzers should be fed from renewable energy sources. And what about future grid architectures? I'll look at three possible scenarios. In the first one, what we see is that the DC grids will dominate, and the DC grid structures, unlike the current situation where they are point-to-point, will be meshed DC networks. This means a need to develop new architectures to allow the deployment of DC grids. However, in the high voltage distribution area, AC networks will be retained. And zooming into the DC grid, what we see is that there will be a proliferation of power electronic converters. In addition to that, unlike the current situation, we have bidirectional power flow, while today in the distribution networks, we only have a unidirectional power flow. This then calls for the development of converters capable of bidirectional power flow and also bidirectional protection. We will also see a proliferation of distributed energy storage systems within the grid. And as a result, suitable energy management techniques need to be developed to ensure that the grid operates correctly. Another possible scenario that has been proposed is one where we have sectionalized a modular grid with AC and DC as well as hybrid microgrids. In this situation also, it's deemed necessary to develop virtual power plants. In addition, microgrids need to be aggregated to form communities of microgrids, which are also referred to as cells. And for this to work correctly, information networks will play a critical role to provide data to guarantee proper functioning of the grid. So from the proposed grid structures, what we see is that electric power will be delivered through hybrid AC and DC grid. We also have dispersed generation with a high percentage of renewable energy sources. AC transmission will be retained for conventional sources and also in the high voltage distribution networks. Voltage source converters will be used to build transmission lines to connect renewable energy sources to the grid, as well as to build the meshed DC networks. The power electronic converters needed will be required to perform various tasks. These include interfacing renewable energy sources to the grid, interfacing storage energy storage system to the grid, realizing bidirectional electronic protection systems, and also sectionalizing transmission system to decouple dynamics. In the distribution networks, most of the loads will be DC, and hence DC power distribution will be necessary. We also have distributed renewable energy sources that utilize DC subsystems, and the grid will be meshed, combining both AC and DC subsystems. It will be beneficial for different categories of subsystems to be introduced. This will facilitate a modular approach to both design and implementation of the future grid. Examples of these subsystems include the following. Subsystem level 1, this consists of loads in a house or the distributed energy storage systems, the distributed renewable energy sources in small buildings or in houses. And in the current literature, these are referred to as picogrids. Then a subsystem level 2, this, for example, a house or a small building. In other words, this will be a cluster of the picogrids, so we can see the modular approach. In the current literature, they are referred to as nanogrids. Then we have subsystem level 3, a cluster of houses, cluster of small buildings or large commercial buildings. In other words, a cluster of nanogrids, and in the current literature, we refer to these as microgrids. And subsystem level 4, this will be a cluster of several microgrids. In the current literature, referred to as cell or macrogrid, and this connects to the high voltage grid. So looking at a subsystem level 2, we see that there will be a central controller which will be employed to integrate the different subsystems. That is the picogrid that are found in the nanogrid. And these are your loads, storage, and the distributed power sources. And also, it will entail bidirectional power flow, which is very much unlike the current situation. And for subsystem level 3, in this case as smart microgrid, there will be a need for communication, power measurement, and sensors to be incorporated, and also the use of smart transformers. This will provide ancillary services, replace transformers with tap changes, and in addition, smart transformers are known to be better at handling faults. The problem at the moment is the high cost of these transformers. The structure of a subsystem level 3 needs to be modular, and there will be a need, therefore, to develop bidirectional converters or converters with bidirectional power flow capability and protection. There will be distributed energy storage systems, and DC distribution will be more efficient if adopted. Still looking at subsystem level 3, what we see is that there will be a need for central controllers to interface the various nanogrids. And the function of this central controller is to ensure that any disturbances emanating from a given nanogrid do not propagate to the other nanogrids where the system should remain healthy. And also, it will be important if each nanogrid that forms the microgrid is capable of operating independently if need be. And looking at our subsystem level 4, the microgrids that form the subsystem level 4, it will be important if they are capable of operating independently if need be. We also see that the reticulation will be DC in nature, and converters will be required to interface the various subsystems, that is the microgrids forming the macro grid. And also it will be important to ensure that any disturbances emanating from a given microgrid are contained within that subsystem so that they do not propagate to other systems of the grid. And looking at the DC transmission systems, what is important here is the need for DC circuit breakers with bidirectional protection capability. And that is something that we do not have at the moment. And the current designs, unfortunately, are still very expensive and not very efficient. So there's a need for further work to be done to bring down the cost and also improve the efficiency. In addition, there will be a need to develop converter topologies that incorporate protection and energy management features within. And if this is done, then the need for the expensive DC circuit breakers will be reduced, and hence bring down the system cost and also improve efficiency. And so what are the challenges arising from wide adoption of renewable energy sources and DC loads? We've seen that the cost and efficiency of DC protection equipment needs to be brought down. Efficiency needs to go up where the cost is brought down. Converters capable of bidirectional power flow and bidirectional protection need to be developed. There's also a need for DC appliances to replace the current AC appliances, and this translates into supply chain disruptions. Transmission and distribution service operators or system operators will have to agree to adopt DC systems. There's a need for standards and regulation for DC systems to be developed. And the reduced inertia as a result of using or employing renewable energy sources and power electronic converters will affect frequency control in the AC grids. In addition, there's a need for an optimal mix of renewable energy sources to minimize energy storage equipment requirements, as these are still very expensive. The Power Research Group has a few activities, or a number of activities that are relevant to future grids. And these include bidirectional smart power control nodes, voltage source-based HVDC systems, some activities on virtual power plants, activities on DC and hybrid microgrids, as well as work on conducted EMI in DC to DC converters. The latter is important as the number of converters increase, then the electromagnetic interference in the grid will increase and hence cause problems. The group has also published a number of articles in journals and conferences, as well as theses that are relevant to the realization of future grids. So in conclusion, we see that to mitigate against climate change, policies that include renewable energy sources in the energy mix are being adopted. We also see that electronic loads are being introduced in all sectors of the economy. Renewable energy sources favor DC distribution systems, while DC loads are best fed from DC sources. Consequently, future grids will most likely entail hybrid AC and DC systems. But for DC transmission and distribution systems to be widely adopted, there's a need for efficient, affordable protection equipment to be developed. There's also a need to determine an optimal mix for renewable energy sources that will minimize storage requirements. Bidirectional power electronic converters capable of performing protection and energy management functions will have to be developed. To also be beneficial to have modular grid architectures, there's a need for innovative solutions to overcome negative effects of deep penetration of renewable energy sources. And the utilities and municipalities will also have to be convinced to the need to change to DC reticulation systems. I thank you for your attention.
Thank you, Professor Gitau, for your very deep and insightful presentation. What you presented, I think, is of critical importance in taking South Africa and the African continent to a new dimension in order to be innovative in our approach, given the energy challenges and the load shedding we face in this country particularly, and of course the impact it has on affecting our economy and investment in the country. And of course, end of the day, it impacts on job creation, poverty, and inequality in the country. I think you also mentioned the very important factors on, of course, going into renewable energies because it's very important in terms of meeting our 17 Sustainable Development Goals, which are very important, and certainly the University of Pretoria places great emphasis on the 17 SDGs and how it aligns its activities both in teaching, in research, and project work to address and to contribute to the 17 Sustainable Development Goals. So certainly I think the work you mentioned and the research opportunities, particularly in DC to DC and related activities, is a lot of work to go forward. And I think it also maps out the research plan and the research activities in the energy space. And University of Pretoria is one of the strong players in the energy space in terms of research. We have quite a strong research group in the university as a whole involved in energy activities and energy research and, of course, consulting and project and technology development. So I also like to thank Professor Kupe for participating in today's inaugural address, given his many commitments and obligations. And of course, special appreciation to the EBIT team under the leadership of our faculty manager, and of course, Ms. Suzanne de Wit, and of course, Emily Marte from our marketing, and all the other marketing colleagues. And of course, we'd like to thank Louis Klute Productions for tonight's production and for you to receive this production and event and live broadcast. And of course, the technical support we got this evening as well. So please be on the lookout for other expert lecture series forthcoming by our esteemed professors at University of Pretoria and in our Faculty of Engineering, Built Environment and Information Technology. Thank you all for attending this inaugural lecture. And of course, very importantly, vaccinate, stay healthy, keep safe, and hope you all have a lovely evening tonight. Good night, take care, and keep well.
Gaudiamus igitur, juvenestum